A single atom of iron inside the human body may once have rested in the core of a dying star. The hydrogen in water is older still, forged only minutes after the universe began. From those first particles, gravity gathers clouds, stars ignite, elements are born, and galaxies slowly take shape across the dark. This journey follows that entire chain from protons and neutrons to stellar furnaces, supernova, planets, and the matter that eventually becomes life. It is a story written at scales too small to see and too vast to fully grasp. Thank you for spending this time here. If this kind of calm, scientific journey brings a little wonder to the day, a like, a subscription, or a share helps it reach others who may enjoy the same quiet experience. What time is it where this is playing, and where in the world is it being watched or heard? Leave a comment below. Now, let the story of how the universe was built begin. The night sky appears to begin with distance. Stars hang beyond reach, galaxies gather in silent swarms, and the darkness between them seems almost empty. Yet the history of this immense structure does not begin with galaxies, or even with stars. It begins with objects so small that no eye can see them directly, objects hidden inside stone, water, air, and every living cell. These objects are atoms, and they form the quiet foundation of the visible universe. Every mountain, ocean, planet, and star is built from them. The scale of the cosmos is almost beyond thought, but its material richness comes from a remarkably limited set of basic forms. The same kinds of atoms found in a human body also exist in drifting clouds between stars, in the crusts of distant worlds, and in the remains of ancient suns. This connection between the smallest and the largest is one of the deepest achievements of modern science. By studying matter inwardly, science learns to read the universe outwardly. The atom becomes a record of creation. For most of human history, atoms remain ideas rather than observed realities. Ancient thinkers suspect that matter may be made from indivisible pieces, but there is no way to prove it. Ordinary experience reveals no hidden grain of matter. Only much later do experiments show that substances combine in fixed proportions, that gases behave as if made of countless moving particles, and that chemical reactions rearrange small, persistent units. By the beginning of the 20th century, atoms no longer seem like useful guesses. They begin to emerge as physical objects with measurable properties. An atom is less than a millionth of a millimeter across, and a single grain of sand contains numbers far beyond ordinary counting. Even a glass of water holds more atoms than there are glasses of water in all the oceans of Earth. Such comparisons reveal how densely the visible world is packed with hidden structure. What appears smooth and simple is crowded with tiny parts. The universe is not made from continuous substance. It is built from innumerable individual units, each obeying rules that remain the same across space. A hydrogen atom in a laboratory behaves like hydrogen in a distant star. An oxygen atom in a breath follows the same laws as oxygen in a glowing nebula. The cosmos can be studied because nature does not invent a new kind of matter for every place. It repeats a small set of patterns with extraordinary consistency. The naturally occurring elements form a sequence, from the lightest hydrogen to the heaviest long-lived nuclei found in nature. Each element has its own identity, yet all are variations on a common design. Hydrogen, helium, carbon, oxygen, iron, gold, and uranium differ not because they are made from entirely separate substances, but because their atoms contain different internal arrangements. Instead of asking how countless unrelated materials appear, science asks how a limited family of atomic structures comes into being. The world of chemistry becomes connected to the history of stars. The iron in rock, the calcium in bone, and the carbon in living tissue are no longer merely earthly materials. They are cosmic products. To understand the universe, it becomes necessary to understand why atoms exist, why there are different elements, and why some are common while others are rare. The answer lies inside the atom itself. At first, the atom is imagined as featureless and indivisible, but experiments soon break that image apart. Matter contains electrically charged particles. Radioactive substances release energy from within their own structure. Certain atoms change spontaneously into other forms. These discoveries show that the atom has an interior, and that the interior is not quiet. It contains stored energy, hidden forces, and particles arranged on a scale even smaller than the atom as a whole. The atom is a small world with its own architecture. At its centre lies a compact nucleus, holding almost all the atom's mass. Around it extends a much larger region occupied by electrons, light particles whose behaviour gives matter its chemical properties. If the atom were expanded to the size of a great building, the nucleus would remain like a speck near its centre, while most of the interior would be open space governed by invisible fields. Solid matter feels solid not because atoms are packed like stones without gaps, but because electrical forces resist the overlap of their electron structures. Familiar solidity arises from interactions inside and between atoms. Familiar reality is therefore built from emptiness, force, and motion. The nucleus deepens the mystery. It contains protons, which carry positive electric charge, and neutrons, which carry no electric charge. The number of protons determines the identity of the element. 1 proton forms hydrogen, 2 form helium, 6 form carbon, 8 form oxygen, 26 form iron, 92 form uranium. This simple counting rule organizes the chemical world. Every naturally occurring element can be placed in order according to the number of protons in its nucleus. Carbon and oxygen differ, at the deepest atomic level, by 2 protons. The difference between iron and gold is a difference in nuclear composition. Nature builds diversity by changing the contents of a space far smaller than the atom itself. Yet this simple rule raises a harder question. If an element is defined by its nucleus, then the origin of the elements must be a history of changing nuclei. Creation becomes a process of nuclear transformation. Atoms are not all formed in the same place or at the same time. The lightest arise under conditions very different from those that produce heavier elements. Some appear in the early universe, others are assembled inside stars. Still others require the violent final moments of massive stars or the collision of dense stellar remnants. The periodic table is therefore also a timeline. Each element points toward a particular environment, temperature, pressure, and stage of cosmic evolution. Hydrogen carries the memory of the young universe. Carbon and oxygen carry the history of long burning stars. Iron records the final productive stages inside massive stellar cores. Gold and many other heavy elements point toward rare events where matter is driven through extremes. The atoms present in a single handful of soil may have formed in several unrelated cosmic settings, separated by billions of years. Atomic structure reveals where energy can be stored, how nuclei can join, how they can split, and why certain arrangements are more stable than others. Those rules determine how stars shine, live, create, and die. They influence the formation of planets and the availability of the elements required for oceans, rocks, atmospheres, and life. The largest visible structures depend on the behavior of the smallest hidden ones. Galaxies may span distances so great that light requires thousands of centuries to cross them, but the light from their stars is generated by changes inside atomic nuclei. Planetary layers differ because of atomic properties and bonds. Living cells may organize matter with extraordinary complexity, but they remain assemblies of elements whose origins lie in cosmic history. The path from atoms to galaxies is not a leap between unrelated scales. It is a continuous chain of cause and consequence. The stars are no longer distant lights with mysterious fuel. They are laboratories where nuclei are transformed. Nebulae are not merely clouds. They are reservoirs of ancient atoms waiting to become new systems. Planets are not isolated worlds made from local material. They are collections of debris inherited from earlier generations of stars. Even the matter inside living bodies becomes part of a much older story. Its atoms survive processes of fusion, explosion, cooling, collision, and assembly before entering oceans, minerals, and cells. Nothing in this history is simple, yet the opening principle is clear. To understand how the universe is built, science begins not with the grandeur of galaxies, but with the hidden structure of atoms. Inside them lie the rules that connect light to matter, stars to elements, and cosmic beginnings to the material world that exists now. The mystery is not merely that atoms exist, but that their rules remain reliable across an expanding cosmos. The same nuclear patterns persist in nearby matter and in light arriving from remote galaxies. That consistency allows ancient events to be reconstructed from present evidence, turning every atom into both material and message, a surviving fragment of processes that began before planets, oceans, or life. The smallest foundations hold the first clues, and within those clues waits a deeper question. If atoms contain the architecture of the visible universe, then what forces shape that architecture, and what keeps the tiny nucleus from tearing itself apart? The atom appears simple only from a distance. Reduced to a symbol in a chemical formula, it can seem indivisible. Yet every atom contains a layered structure shaped by charge, mass, motion, and probability. At the center lies the nucleus, a region so small that almost all of the atom's volume exists outside it, and yet almost all of the atom's mass is concentrated within it. Around that dense center spreads the domain of electrons, whose motions and arrangements govern how atoms meet, bond, separate, and combine. The visible world begins to take form through this hidden division of labor. The nucleus decides what an atom is. The electrons decide how that atom behaves. The nucleus contains protons and neutrons. Protons carry positive electric charge, while neutrons carry no net charge. Their masses are nearly equal, and together they account for almost everything that can be weighed in an atom. Electrons are far lighter, but their influence is enormous. Each electron carries a negative electric charge, balancing the positive charge of the protons when the atom is electrically neutral. This balance creates an object that, from the outside, often appears uncharged, even though it is built from charged parts. The number of protons remains the central rule. An atom with 1 proton is hydrogen. With 2 protons it is helium. With 6 it is carbon. With 8 it is oxygen. With 26 it is iron. Change the number of protons, and the element itself changes. Remove a neutron, or add a neutron, and the element may remain the same, though its mass and stability may shift. Remove or add an electron, and the element still remains the same. But it becomes an ion, an atom carrying electrical charge. These distinctions give the atomic world both order and flexibility. The earliest atomic models picture electrons moving around the nucleus like planets around a star. The image is useful, but it soon proves incomplete. Electrons do not travel along neat circular paths that can be traced from moment to moment. Their behavior belongs to quantum physics, where certainty gives way to probability. An electron is described not as a small ball following a visible orbit, but as a spread of possible locations, a cloud of likelihood surrounding the nucleus. Some regions are more probable than others. These regions form orbitals, distinct patterns in which electrons can exist. These orbitals determine how atoms connect and how chemistry unfolds. Electrons occupy energy levels, and each level has room for a limited arrangement. The lowest levels fill first. As more electrons are added, they settle into larger and more complex patterns. The outermost electrons are especially important because they are the ones most available for interaction. Atoms with nearly full outer levels tend to attract electrons. Atoms with only a few outer electrons tend to release or share them. From this simple tension comes an enormous variety of matter. Sodium and chlorine form salt because one tends to give up an electron while the other tends to accept it. Carbon forms the basis of life because its outer structure allows it to form several stable bonds in many different arrangements. Oxygen reacts readily because its electron pattern strongly favours completion. The architecture of electron states becomes the architecture of crystals, minerals, gases, liquids, cells, and bodies. The periodic table is a map of this repeating electronic order. Elements arranged in columns often behave similarly because they possess similar outer electron structures. The patterns repeat as each energy level fills, turning a list of substances into families. Noble gases resist chemical change because their outer electron structures are already complete. Alkali metals react strongly because they hold a single outer electron loosely. Halogens react strongly for the opposite reason. Because they lack only one electron in an otherwise nearly complete outer level. The order of the table reflects the order within atoms. Chemical behavior is therefore not accidental. It emerges from recurring internal patterns. Yet the nucleus remains more mysterious than the electron cloud. Protons crowd together within a space vastly smaller than the atom, even though their positive charges repel one another. Neutrons add mass without adding electrical repulsion, and their presence often helps stabilize the nucleus. The same element can exist with different numbers of neutrons. These forms are isotopes. Carbon, for example, always contains 6 protons, but its isotopes contain different numbers of neutrons. Some isotopes are stable, others are unstable and gradually transform through radioactive decay. This instability is not a defect but a natural consequence of nuclear balance. A nucleus may contain too many neutrons, too few, or too many protons for its arrangement to remain secure. When the balance fails, particles or radiation are released, and the nucleus moves toward a more stable state. Radioactivity reveals that atoms are not eternal and unchangeable. Some survive for times far longer than the age of the universe. Others last only brief fractions of a second. The lifetime depends on nuclear structure. These differences make isotopes powerful tools, preserving records of ancient climates, water cycles, and biological processes. Radioactive isotopes act as natural clocks because they decay at measurable rates. By comparing the remaining unstable material with its decay products, science can estimate the ages of rocks, fossils, meteorites, and planetary surfaces. The atomic nucleus therefore becomes a keeper of time. It preserves histories that no written record could hold. The electron cloud carries another kind of information. When electrons absorb energy, they move into higher states. When they return to lower states, they release that energy as light. The light appears only at specific wavelengths, corresponding to precise differences between electron energy levels. Each element therefore produces a distinct pattern of spectral lines, a kind of atomic signature. When starlight is separated into its colors, dark and bright lines reveal which elements are present. No sample is required. The atom announces itself through light. Hydrogen leaves one pattern, helium another, iron another. The same structures measured in laboratories on Earth appear in stars and nebulae across the galaxy. This agreement shows that atomic laws are not local accidents. They hold across immense distances and through deep time. Spectroscopy turns light into evidence. From a faint beam arriving after thousands or millions of years, the composition, temperature, motion, and density of distant matter can be inferred. The inner structure of atoms becomes a language written across the sky. The strangeness deepens when scale is considered. Most of an atom is not filled with solid material in the ordinary sense. The nucleus occupies only a minute fraction of the total volume. Electrons spread through regions that are better understood as quantum states than as tiny objects circling through empty rooms. Matter feels continuous because enormous numbers of atoms interact through electromagnetic forces. The hand does not pass through a table because the electron structures of the atoms resist one another, not because every point in the table is packed with dense substance. Solidity is an effect of force and quantum rules. The familiar world is stable because invisible structures prevent atoms from collapsing into one another, while remaining flexible enough for bonds, phase changes, electricity, magnetism, and life. Matter is neither rigidly fixed nor freely chaotic. It exists in a narrow region where forces and quantum restrictions create dependable forms. The atom is therefore not merely a piece of an element, but a system held together by several layers of law. The proton count establishes identity. Neutrons influence mass and stability. Electrons shape chemistry and light. Quantum rules determine where electrons may exist and how they may change. Nuclear rules determine whether the center endures or decays. Each layer connects to the next. A small shift in the nucleus can alter stability. A small shift in electron arrangement can change reactivity. A single absorbed packet of energy can move an electron and later produce a photon. From such small events come fire, color, electricity, metabolism, and the light of stars. The atomic world is not separate from the cosmic world. It is the mechanism through which the cosmic world becomes visible. Yet one central difficulty remains. The nucleus contains positively charged protons compressed into extraordinary closeness. Electrical repulsion should drive them apart. Neutrons alone cannot explain why the nucleus holds. Something else must act at very short range, something strong enough to overcome the force that pushes protons away from one another. The stability of matter depends on this hidden binding power. Without it, the elements beyond hydrogen could not persist. Stars could not build heavier nuclei, and the universe would never develop the chemical richness required for planets or life. The architecture of the atom therefore leads directly toward a deeper force, one that works only across tiny distances but shapes the entire history of matter. The atomic nucleus is a place of extreme contradiction. It is unimaginably small, yet it contains nearly all the mass of the atom. It holds protons that carry the same positive charge, even though objects with the same charge repel one another. Packed within the nucleus, those protons should push apart with enormous force. A nucleus containing many protons appears, at first, to be an impossible structure. Its continued existence means that another influence must be acting, one stronger than electrical repulsion at the shortest distances. That influence is the strong nuclear force, a binding power so intense that it makes stable matter possible. Its range is tiny, but its consequences extend from the heart of the atom to the structure of stars and the history of galaxies. The electric force between protons acts across long distances compared with the nucleus. It weakens as separation grows, but it never truly ends. The strong nuclear force behaves differently. It becomes important only when protons and neutrons come extremely close together. At those distances, it overwhelms the electric repulsion and locks the particles into a compact arrangement. The effect resembles a bond that does not reach outward very far, but becomes overwhelming once the particles are nearly touching. This short range is essential. If the strong force extended far beyond the nucleus with the same power, matter would behave in a radically different way. Separate atoms might collapse into larger nuclear masses, and ordinary chemistry could not exist. Instead, the strong force remains confined to the interior of nuclei, where it provides enough binding to create the elements. Protons and neutrons are collectively called nucleons because both participate in nuclear structure. The strong force acts between proton and proton, neutron and neutron, and proton and neutron. Within the nucleus, each nucleon mainly interacts with its closest neighbours. This local behaviour means that adding more nucleons does not increase binding without limit. A large nucleus gains attraction from nearby particles, but every added proton also increases electrical repulsion across the entire nucleus. The result is a delicate competition. In small nuclei, the strong force easily holds the structure together. In larger nuclei, the growing electric pressure makes stability harder to maintain. Neutrons help because they contribute to the strong attraction without adding positive charge. They increase cohesion while avoiding further electrical repulsion. For light elements, stable nuclei often contain similar numbers of protons and neutrons. As nuclei grow heavier, they usually require proportionally more neutrons to remain stable. The extra neutrons provide additional attraction and help separate the protons, though they cannot solve the problem forever. Beyond a certain size, no arrangement remains completely secure. The heaviest nuclei become radioactive, changing over time as they seek more stable forms. Nuclear stability is not determined by size alone. The arrangement of nucleons also matters. Protons and neutrons occupy quantum states within the nucleus, following rules that limit how they can be placed. Certain combinations produce unusually stable structures. Others leave the nucleus vulnerable to decay. The nucleus is therefore not a simple cluster of tiny balls. It is a quantum system in which force, motion, energy, and arrangement all contribute to survival. Even so, the image of competing influences remains useful. The strong force pulls nucleons together over very short distances. Electrical repulsion pushes protons apart. Quantum rules shape the available configurations. Stability appears where these demands find a workable compromise. When that compromise fails, the nucleus transforms. It may release an alpha particle, which consists of 2 protons and 2 neutrons bound tightly together. It may convert a neutron into a proton, or a proton into a neutron through beta decay. It may release excess energy as gamma radiation. Each form of decay changes the nucleus in a particular way, moving it toward a lower energy condition. Radioactivity is therefore not random destruction. It is a path through the landscape of nuclear possibilities. Some steps happen almost instantly, while others require immense periods. A nucleus may survive for less than a heartbeat, or for longer than planets have existed. The difference comes from how difficult it is for the nucleus to cross from one arrangement into another. The strong force also explains why nuclear reactions release so much energy. When nucleons bind together, the final nucleus can have slightly less mass than the separate particles that formed it. The missing mass has been converted into binding energy and released, often as radiation or motion. A tiny change in mass corresponds to an enormous amount of energy, because mass itself is a concentrated form of energy. Chemical reactions involve changes in electron arrangements, so their energies are comparatively modest. Nuclear reactions rearrange the deeply bound contents of nuclei, and the energies are vastly greater. This difference allows stars to shine for billions of years, and nuclear decay to remain detectable across geological time. The strong force, however, is not the most fundamental description of what happens inside protons and neutrons. Each proton and neutron is made from smaller particles called quarks. Quarks carry a property known as color charge, which has no connection to visible color. They interact through a more basic force described by quantum chromodynamics. The carriers of this force are gluons, particles that bind quarks together with extraordinary strength. A proton contains a restless interior of quarks, gluons, and temporary particle pairs. Most of its mass does not come directly from the small intrinsic masses of its quarks. It arises from the energy of their motion and interaction. The strong nuclear force between protons and neutrons is a residual effect of this deeper quark binding. The nucleus is therefore built from layers of confinement. Quarks are confined inside nucleons, and nucleons are bound inside nuclei. At each level, energy and force create stable forms from smaller moving parts. One of the strangest features of quark binding is that the force does not weaken, as quarks separate in the ordinary way. Pulling quarks apart requires increasing energy. Before a single quark can be isolated, enough energy is stored to create new particles, leaving quarks still confined inside composite objects. No free quark has been observed under normal conditions. The attempt to separate them produces more bound matter instead. This behavior gives protons and neutrons their durability. Yet stability never means complete stillness. The nucleus is dynamic. Nucleons move within a confined quantum system, and the forces between them fluctuate. The image of particles resting in fixed positions is misleading. The nucleus is better understood as a dense, vibrating structure whose components occupy allowed states. Its size, shape, and energy can change. Some nuclei are nearly spherical, others are stretched or deformed. Some can be excited into higher energy arrangements before releasing radiation and settling again. Under extreme conditions, nuclei may rotate, oscillate, collide, merge, or tear apart. These possibilities become important inside stars where temperature and pressure bring nuclei close enough to react. The same strong force that binds a nucleus also creates a barrier to fusion. Two positively charged nuclei repel each other before they reach the distance where the strong force becomes dominant. In a star, high temperature gives nuclei rapid motion, while immense pressure keeps them crowded together. Quantum tunneling allows some nuclei to pass through the electrical barrier even when classical motion would not provide enough energy. Once they approach closely enough, the strong force takes control and joins them into a new nucleus. The energy released from this binding becomes part of the light and heat of the star. Nuclear stability therefore shapes the direction of stellar evolution. Light nuclei can release energy by fusing into more tightly bound forms. Very heavy nuclei can release energy by splitting into smaller, more stable pieces. Between these regions lies a group of exceptionally stable nuclei near iron and nickel. They mark a turning point in the nuclear landscape. Fusion toward this region can produce energy, but fusion beyond it generally requires energy instead. This hidden pattern determines how long stars burn, what elements they create, and what happens when their fuel is exhausted. The glow of a star is the visible expression of a struggle taking place across distances far smaller than an atom. Gravity compresses the stellar core. Electrical repulsion resists approaching nuclei. Quantum tunneling opens rare paths through the barrier. The strong force binds successful collisions into heavier forms. Energy escapes and eventually becomes starlight. The stability of worlds depends on the same balance. Without the strong force, there would be no carbon, oxygen, silicon, calcium, or iron. Without electrical repulsion, nuclei might collapse into featureless masses. Without quantum restrictions, atomic structures would lose their order. Matter exists because these influences neither cancel completely nor dominate everywhere. They divide nature into scales, allowing nuclei to be dense, atoms to be spacious, molecules to be varied, and galaxies to be built from stable material. The nucleus is not merely held together, it is held at the edge of competing possibilities. And from that tension comes the diversity of the elements. At the centre of every ordinary star, darkness is transformed into light by events too small to be seen and too numerous to count. The surface may glow across a distance of millions of kilometres, yet the source of that brightness lies in collisions between atomic nuclei, each one smaller than the atom that surrounds it. A star shines because gravity gathers matter inward, compressing gas until pressure and temperature become immense. In that crowded interior, hydrogen nuclei move with extraordinary speed. Most pass one another without reacting. Their positive charges repel, creating an electrical barrier between them, yet a small fraction approach closely enough for the strong nuclear force to take hold. When that happens, separate nuclei become a new, more tightly bound structure, and part of their mass emerges as energy. This process is nuclear fusion, the quiet engine beneath starlight. Hydrogen is the natural beginning because it is the simplest and most abundant element in the universe. Its ordinary nucleus contains only a single proton. In the young cosmos, vast clouds of hydrogen gather under gravity, and as they contract, their central regions become hotter and denser. Gravity does not simply pull matter together. It converts the energy of falling material into heat. The more the cloud contracts, the faster its particles move. At first, the object remains a dark protostar, glowing only faintly from compression. As the core grows hotter, collisions between nuclei become more energetic and frequent. Eventually, conditions reach a threshold at which fusion can continue steadily. The star ignites, not as a sudden flame, but as a stable nuclear process that may endure for millions or billions of years. The reaction begins with a difficulty. Protons repel one another, and the temperatures inside stars are not high enough for most collisions to overcome this barrier directly. Classical physics would suggest that fusion should be extremely rare. Quantum physics provides the missing path. Particles do not behave only as small, solid objects. They also possess wave-like properties, and their positions cannot be described with perfect certainty. This allows a phenomenon called quantum tunneling. A proton may appear on the far side of an energy barrier that it could not cross in a purely classical world. The chance is small, but the number of protons in a stellar core is enormous. Even rare events become continuous when matter is dense enough and time is long enough. In stars like the Sun, fusion proceeds mainly through a chain of reactions known as the proton-proton chain. Two protons approach, tunnel through their electrical barrier, and come under the influence of the strong force. One proton changes into a neutron through the weak nuclear force, producing a nucleus of heavy hydrogen called deuterium. This first step is extremely slow, and that slowness is essential. If it occurred easily, stars would consume their fuel rapidly and burn with violent intensity. Instead, the weak force makes the opening reaction rare, allowing a star like the Sun to shine steadily over an immense span of time. The pace of stellar life depends on the difficulty of this first transformation. Once deuterium exists, it can combine with another proton to form helium-3, releasing energy. Two helium-3 nuclei can later merge, producing helium-4 and returning two protons to the surrounding plasma. The overall result is that 4 hydrogen nuclei have been transformed into one helium nucleus. The final helium nucleus has slightly less mass than the 4 original protons. That difference has not vanished. It has become energy, carried away by radiation, particle motion, and nearly massless particles called neutrinos. The mass difference is small, but the energy released from countless reactions is enough to support the star against collapse and illuminate the surrounding system. Fusion therefore links nuclear structure to gravity. Gravity continuously presses inward, attempting to compress the star. Energy from fusion heats the interior, creating pressure that pushes outward. For much of a star's life, these influences reach a dynamic balance called hydrostatic equilibrium. The star does not become motionless. Energy flows through it, matter circulates, and nuclei continue to change. Yet its overall size remains comparatively stable because inward gravity and outward pressure nearly match. This balance can last only while usable. Nuclear fuel remains in the core. Starlight is a delayed messenger from that hidden struggle. Energy produced near the center does not travel directly to the surface in a simple beam. In the dense interior, photons are absorbed and re-emitted again and again, changing direction through countless interactions with charged particles. Their outward journey may require an immense span of time. Closer to the surface, energy may also be carried by convection, with hot material rising while cooler material sinks. Only after this long passage does radiation escape into space. The visible light crossing a planetary system therefore begins as nuclear energy deep inside the star is repeatedly transformed within stellar matter, and finally emerges from the photosphere as a broad spectrum of color. Some of the energy escapes in a different form. Neutrinos interact so weakly with matter that they pass almost directly through the star. They leave the core within moments and travel through planets, oceans, and living bodies with almost no disturbance. Their detection provides a rare, immediate view of fusion at the center of the Sun. Light reveals the surface after a complicated journey. While neutrinos carry evidence from the nuclear reactions themselves, together they confirm that the star is not burning through chemical fire. Its power comes from changes in atomic nuclei. The Sun converts hundreds of millions of tons of hydrogen into helium each second, but its total mass is so great that this rate can continue for billions of years. Only a fraction of the available hydrogen lies in regions hot enough to fuse during the main part of its life. The slow pace and limited core protect the star from exhausting itself too quickly. The energy output also regulates the reaction. If the core begins to heat, pressure increases and the star expands slightly. Expansion cools the core and slows fusion. If the core cools, gravity compresses it more strongly, raising the temperature and increasing the reaction rate. This natural feedback gives ordinary stars remarkable stability. Fusion is self-regulating within a broad range of conditions. The light from a star carries the signature of this internal structure. Its color depends largely on surface temperature, while its brightness reflects size, temperature, and energy production. Spectral lines reveal which atoms are present in the outer layers. Changes in brightness, vibration, and surface motion allow the hidden interior to be studied. Even the smallest nuclear reactions leave large-scale signs. The energy generated in the core controls the star's radius, lifetime, color, and future. A low-mass star burns hydrogen slowly and may survive for far longer than the present age of the universe. A massive star compresses its core more fiercely, reaches higher temperatures, and uses its fuel at a much faster rate. Greater mass produces greater luminosity, but also a shorter life. The most brilliant stars are not the most enduring. Their intense light is evidence of rapid consumption. Fusion also changes the chemical composition of the stellar core. Hydrogen gradually declines as helium accumulates. Because helium nuclei contain more mass and charge than hydrogen nuclei, the core's physical conditions slowly change. The star adjusts by becoming hotter and denser, and its energy output gradually shifts. Even during the apparently stable main sequence stage, a star is evolving. Its light is the visible surface of a slow internal transformation. The balance remains calm only because change proceeds steadily rather than suddenly. Every photon released into space is part of that long process. carrying energy created by the movement of nuclei toward greater binding. On planets, starlight drives climates, powers photosynthesis, warms oceans, and shapes atmospheres. Yet its origin remains nuclear. The warmth falling on a leaf begins with protons tunneling through an electrical barrier in the core of a star. The visible world is sustained by events occurring at scales far below direct perception. Fusion turns the simplest element into a heavier one, converts a small amount of mass into radiation, and holds gravity in temporary balance. It is both a source of stability and the beginning of change. Once the hydrogen in the core is depleted, the balance must be rebuilt under new conditions. The star contracts, heats, and prepares to fuse heavier nuclei. Starlight therefore contains a warning as well as a gift. The same process that allows a star to shine also alters the fuel on which its stability depends. The light is steady, but the star is not eternal. Within every calm stellar glow, the nucleus is moving toward the next stage of cosmic construction. The elements do not all occupy the same place in the hidden economy of the nucleus. Some nuclei hold their protons and neutrons more tightly than others, and this difference determines whether a nuclear reaction releases energy or demands it. At one end of the sequence stand the lightest elements, especially hydrogen and helium. Their nuclei can combine into heavier forms and become more tightly bound, releasing energy in the process. At the other end stand very heavy elements, whose enormous nuclei contain so much internal electrical repulsion that they can release energy by splitting into smaller pieces. Between these regions lies a broad summit of nuclear stability, and near its peak stands iron. It is not the heaviest element, yet it marks one of the most important boundaries in the universe. The path of energy inside stars bends around it. To understand why, the nucleus must be considered not only as a collection of particles, but as a reservoir of binding energy. When protons and neutrons join, the resulting nucleus weighs slightly less than the separate particles from which it forms. The missing mass appears as energy. The more tightly the nucleus is bound, the more energy has been released during its creation. Nuclear physicists describe this stability through binding energy per nucleon, a measure of how strongly each proton or neutron is held within the nucleus. Light nuclei generally become more tightly bound as they fuse into heavier ones. This trend continues through carbon, oxygen, neon, magnesium, silicon, and other elements produced in stars. Each stage moves matter toward greater stability, and the difference in binding energy emerges as heat and radiation. Yet the trend cannot continue forever. The strong nuclear force acts only over very short distances, while electrical repulsion between protons reaches across the nucleus. In a small nucleus, almost every nucleon remains close enough to benefit strongly from its neighbours. In a larger nucleus, distant parts do not share the same attraction, but the protons continue to repel one another across the whole structure. As the nucleus grows, the gains from adding more nucleons begin to diminish. Stability rises, approaches a maximum, and then slowly falls. The exact summit belongs to nuclei near iron and nickel, where the balance between attraction and repulsion becomes exceptionally favourable. Iron often serves as the symbol of this peak because of its abundance, its role in stellar cores, and its central place in the sequence of fusion. The distinction between iron and nearby nickel isotopes is important, but the broader principle remains the same. Matter near this region is bound with unusual strength. A star can release energy by building nuclei toward that region, but not by pushing far beyond it through ordinary fusion. This hidden limit governs the life of every massive star. After a star consumes hydrogen in its core, gravity compresses the growing helium. The temperature rises until helium nuclei begin to fuse, producing carbon and oxygen. In more massive stars, the core later becomes hot enough for carbon fusion, followed by stages involving neon, oxygen, and silicon. Each stage occurs under harsher conditions and lasts for a shorter time than the one before it. Hydrogen burning may continue for millions of years in a massive star. Helium burning lasts far less. Carbon burning may continue for centuries. Later stages can shrink to months, days, or even less, because the reactions become faster while the available fuel and energy return decline. The star develops layers around its center, with different elements fusing in shells at different depths. Hydrogen burns farther out, helium beneath it, and progressively heavier fuels occupy hotter regions closer to the core. The structure resembles nested zones of nuclear history, each one preserving a stage that the center has already passed. Deep inside, silicon fusion does not proceed as a simple joining of two large nuclei. At the extreme temperatures of the final stellar stages, high-energy photons repeatedly break nuclei apart, while particles are captured and exchanged in a dense network of reactions. Matter moves through many unstable forms before settling into nuclei near the iron peak. The process is complicated, but its direction is clear. The core is being driven toward the most tightly bound region available. With each earlier fuel, fusion releases energy that helps support the star against gravity. When the central material becomes dominated by iron group nuclei, that source of support changes fundamentally. Fusing iron does not provide a useful energy gain. It generally requires energy because the products lie beyond the summit of binding stability. The star has reached a nuclear dead end. Iron is therefore not merely another product in the sequence. It is the point where ordinary stellar fusion ceases to be a source of power. For most of a massive star's life, gravity and fusion oppose one another. Gravity compresses the core, raising the temperature. Fusion responds by releasing energy, generating pressure, and slowing the collapse. Once iron accumulates, compression can no longer awaken a new exothermic fuel in the same way. Higher temperatures do not solve the problem. They can instead become destructive. Energetic photons begin to break iron nuclei apart in a process called photodisintegration, consuming energy rather than producing it. Electrons are also driven into protons, creating neutrons and neutrinos. This electron capture reduces the pressure contributed by electrons, while escaping neutrinos carry energy away. Several supports weaken almost at once. The iron core grows until it can no longer resist gravity. Its collapse occurs because iron is too stable to offer further energy through fusion. Its exceptional binding closes the path that previously sustained the star. The element associated with strength in the material world becomes, in the stellar interior, a sign that the old balance is ending. The boundary near iron also explains why nuclear fission works in the opposite direction for the heaviest elements. Uranium and other massive nuclei lie beyond the peak of stability. When one of these nuclei splits into medium-sized fragments, the products are more tightly bound per nucleon. The difference appears as released energy. Fusion and fission are therefore movements across the same landscape. Light nuclei release energy by climbing toward the iron region through fusion. Very heavy nuclei release energy by moving back toward it through fission. The peak provides a single framework for understanding both processes. It also reveals why no unlimited source of energy can be gained by simply joining nuclei forever. Nature offers energy only when a reaction moves matter toward a more tightly bound arrangement. Once the summit is reached, the direction changes. Iron's importance extends beyond stellar collapse. Its abundance reflects both nuclear stability and the repeated production of iron group elements in massive stars and stellar explosions. Within rocky planets, iron's density and chemical behavior cause much of it to sink toward the interior during early melting. Earth develops a metallic core rich in iron, and motion within its liquid outer region helps generate the planet's magnetic field. Iron also enters minerals, colours rocks, carries oxygen in blood through complex molecules, and participates in biological chemistry. Its presence in planets and living systems begins with nuclear events far from those later environments. Every iron atom carries a history of stellar transformation, but that history does not always end at the moment of core fusion. Some iron group nuclei are first produced as unstable isotopes, especially forms of nickel that later decay through intermediate stages into stable iron. The final abundance emerges through both fusion and radioactive change. The iron found in a planet may therefore be the settled remainder of a chain that begins in the final burning stages of a massive star and continues after the star explodes. Iron is both an endpoint and a survivor. It ends one route of energy production while enduring as a common ingredient of later worlds. Yet the Iron Peak does not explain the origin of every heavier element. Gold, platinum, uranium, and many others lie beyond the point where ordinary fusion releases energy. Their creation requires environments with exceptional supplies of neutrons, intense radiation, rapid capture processes, or explosive flows of energy. A star cannot build them during stable burning merely by continuing the same sequence. Something more violent or unusual must occur. The appearance of iron in a massive stellar core therefore signals two transitions at once. It marks the end of sustained fusion as the star's central support, and it prepares the conditions for events capable of creating and dispersing heavier matter. The nuclear landscape narrows toward a summit, and at that summit the calm engine of starlight reaches its limit. One element stands at the boundary between long stellar life and sudden collapse, between energy gained by fusion and energy required for further construction. Iron does not end the story of the elements, but it ends the easy path. Beyond it, the universe must find more extreme ways to build. The earliest elements are born before there are stars, planets, or galaxies. They emerge during a brief interval when the universe is still hot enough for atomic nuclei to form, yet cool enough for some of those nuclei to survive. In that beginning, matter does not resemble the familiar world. There are no atoms with electrons arranged around stable centers. There are no molecules, no grains of dust, and no solid surfaces. Space itself is expanding, carrying matter and radiation outward while the temperature falls. Only the lightest nuclei can appear in those conditions. Hydrogen, helium, and small traces of a few other light elements become the first durable material structures in cosmic history. Their abundances preserve a record of the universe when it is only minutes old. In the earliest fraction of time, temperature is so high that particles are constantly created, destroyed, and transformed. Quarks and gluons exist in a dense, energetic state before quarks become confined inside protons and neutrons. As expansion continues, the universe cools enough for these nucleons to persist. Protons and neutrons then move through a sea of radiation and other particles. Their relative numbers are shaped by reactions involving the weak nuclear force. Neutrons can become protons, and protons can become neutrons, but the balance gradually shifts because neutrons are slightly heavier. As the temperature falls, reactions that maintain this exchange become less frequent, and protons become more common than neutrons. This imbalance determines what can be built later. The small excess of protons becomes the foundation of cosmic hydrogen. Yet nuclei cannot form immediately. Protons and neutrons may combine to make deuterium, a heavy form of hydrogen containing one proton and one neutron, but energetic photons quickly tear it apart. The universe is filled with radiation powerful enough to destroy these fragile nuclei almost as soon as they appear. This delay is known as the deuterium bottleneck. It prevents the assembly of heavier nuclei until the temperature has fallen sufficiently. The universe expands and cools while protons and neutrons wait. When deuterium finally begins to survive, nuclear reactions proceed rapidly. Deuterium captures additional protons and neutrons, forming helium-3, tritium, and eventually helium-4. Helium-4 contains 2 protons and 2 neutrons in a tightly bound arrangement. Its stability makes it the dominant product of primordial nucleosynthesis, the name given to the creation of nuclei in the early universe. Most available neutrons become locked inside helium-4 because free neutrons are unstable and decay if they remain unbound for too long. Once those neutrons are captured, the remaining protons persist mainly as hydrogen nuclei. The result is a universe composed mostly of hydrogen, with a substantial amount of helium and only tiny traces of other light nuclei. By mass, roughly 3/4 of ordinary matter is hydrogen, and about 1/4 is helium. The broad pattern is ancient. It is established before the first star shines. This first era of element formation lasts only a short time. The universe cools so quickly that fusion cannot continue toward carbon, oxygen, or iron. The density drops, collisions become less common, and the nuclear reactions cease. There is also a structural obstacle. Stable nuclei with certain small numbers of nucleons are missing from nature, creating gaps in the path toward heavier elements. There is no efficient way to bridge those gaps. Stars later bridge them by bringing 3 helium nuclei together through a sequence that produces carbon. The early universe has neither enough time nor the right conditions for that process to operate widely. Its nuclear furnace is intense but brief. It produces simplicity rather than diversity. Small amounts of deuterium, helium-3, and lithium also survive. These rare nuclei become especially valuable because their abundances depend sensitively on the conditions of the young universe. Deuterium is easily destroyed inside stars and is not produced in large amounts by ordinary stellar fusion. Its presence therefore acts as a fossil from primordial nucleosynthesis. By measuring deuterium in ancient gas clouds that have undergone little stellar processing, astronomers can estimate how much ordinary matter existed during the first minutes. Helium provides another test, while lithium presents a more difficult puzzle. The observed amount of primordial lithium in old stars does not align perfectly with the simplest theoretical predictions. This may reflect stellar changes, observational limits, or physics not yet understood. The disagreement remains a reminder that even a well-supported cosmic history can preserve unresolved details. Primordial nucleosynthesis is powerful because it connects nuclear physics measured in laboratories with observations of the oldest accessible matter. The reaction rates of light nuclei can be studied experimentally. The expansion rate of the young universe can be calculated from its energy content. When these elements are combined, the predicted abundances of hydrogen, helium, and deuterium closely match what is observed. This agreement is one of the strongest pieces of evidence that the early universe passes through a hot, dense state. It does not describe an explosion expanding into empty space. The expansion is the stretching of space itself, occurring everywhere. Matter does not fly from a central point into a void. Every region moves away from distant regions as the scale of the universe grows. The first elements form throughout that expanding cosmos. There is no unique center where creation happens. The chemistry of the universe begins everywhere at once. Even after nuclei form, complete atoms do not yet exist. The temperature remains too high for electrons to remain bound to nuclei. Matter takes the form of plasma, a mixture of free nuclei and electrons through which light scatters constantly. Hydrogen and helium nuclei are present, but the universe remains opaque because photons cannot travel far without interacting with charged particles. Hundreds of thousands of years must pass before expansion lowers the temperature enough for electrons to settle into stable atomic states. That later transition releases light to travel freely across space, creating the background radiation that still fills the cosmos. The elemental composition is therefore fixed long before the universe becomes transparent. Nuclei come first. Neutral atoms arrive much later. The first hydrogen is not created inside stars. Stars inherit it. Every later generation of cosmic structure begins with this primordial reservoir. Gravity gathers hydrogen and helium into growing regions of density. These regions become the raw material of the first stars, whose fusion then begins the long construction of heavier elements. The universe enters stellar history already carrying the products of its first minutes. This fact corrects an intuitive but incomplete picture in which stars make everything. Stars make much of the periodic table, but they do not create the original supply of hydrogen, and they are not responsible for most of the helium that exists. Those light elements predate every stellar furnace. They are relics of conditions no star can reproduce on a universal scale. Their simplicity is the starting point from which later complexity grows. Hydrogen provides long-lived stellar fuel. Helium becomes a stepping stone toward carbon. Their abundance controls how the first stars form, how quickly they evolve, and what kinds of elements they eventually release. A difference in the primordial mixture would alter the later universe. Too few neutrons would reduce helium production. Too many would leave less hydrogen for long-burning stars. The observed balance creates a cosmos in which stars can shine steadily, and chemical evolution can unfold over billions of years. The first elements therefore shape everything that follows without resembling the later structures they enable. They exist before galaxies, yet they influence galaxies. They exist before planets, yet they supply the stars that enrich planetary systems. They exist before life, yet hydrogen becomes part of water, and helium helps open the nuclear path toward carbon and oxygen. The beginning of chemistry is almost austere, a universe dominated by two elements and marked by traces of a few others. Within that narrow inventory lies the potential for every later atom. The first minutes do not build the full periodic table. They establish the material grammar from which stars will compose it. Long after the early fire has faded, hydrogen and helium remain everywhere, filling stars, drifting through interstellar space, and surrounding galaxies in vast clouds. Their abundance is a memory that matter has never lost. Yet the young universe still holds another record, not in nuclei but in light. When electrons finally join those nuclei and the cosmos becomes transparent, radiation begins a journey that continues across nearly all of cosmic history. That ancient afterglow preserves an image of the universe before stars and galaxies fully emerge, waiting to reveal how the first elements pass from a hot beginning into a visible sky. For hundreds of thousands of years after the first nuclei form, the universe remains hidden behind its own brightness. Matter exists as a hot plasma of free electrons and atomic nuclei, and light cannot travel far without being scattered. Photons move constantly, but their paths are interrupted again and again by charged particles. The cosmos is filled with radiation, yet it is not transparent. There are no clear distances, no visible stars, and no open darkness between objects. Space is expanding, temperature is falling, and the earliest elements are waiting for the moment when electrons can finally settle around nuclei. When that moment arrives, the universe changes in a way that can still be observed. Light is released from its long imprisonment and begins to travel freely. That light survives today as the cosmic microwave background, a faint afterglow spread across the entire sky. It is the oldest light that can be observed directly. carrying an image of the universe long before galaxies take their mature forms. The release of this radiation does not occur at a sharp wall or a single instant, but over a relatively brief period called recombination. They are joining into neutral atoms for the first sustained time. As the temperature falls, energetic photons become less able to tear electrons away from nuclei. Protons capture electrons and form neutral hydrogen. Helium nuclei also acquire electrons. With fewer free charge particles available to scatter light, photons begin to move across great distances. The universe becomes transparent. The radiation that escapes carries a record of the temperature, density, and motion of matter at that stage. It does not show the first instant of creation. Earlier conditions remain hidden because the plasma is opaque. Instead, it reveals the surface from which ancient photons last scatter before beginning their long journey. This surface surrounds every observer, not because Earth occupies a central position, but because light arriving now has travelled from regions at a particular distance in every direction. The background is not a physical shell enclosing the universe. It is a horizon in time, shaped by the finite speed of light and the expansion of space. When the photons first travel freely, their radiation is far hotter and more energetic than it appears today. The universe continues to expand, stretching the wavelengths of the light along with space. Radiation that once belongs mainly to visible and infrared energies is gradually shifted into the microwave region. Its temperature falls until it becomes only a few degrees above absolute zero. The signal is weak, but it fills space almost uniformly. Every direction carries nearly the same ancient glow. This remarkable smoothness shows that the early universe is close to thermal balance across immense regions. Matter and radiation share nearly the same temperature, and density differs only slightly from place to place. Yet those slight differences are essential. A perfectly uniform universe would remain smooth, with no preferred locations for gravity to gather matter. The background radiation contains tiny variations in temperature, small enough to require sensitive instruments, but large enough to reveal the seeds of later structure. Slightly denser regions exert stronger gravitational attraction. Over time, they draw in more matter, growing into the networks from which galaxies and clusters emerge. Slightly thinner regions lose matter and become cosmic voids. The great structure of the present universe begins as a pattern of minute irregularities recorded in ancient light. The cosmic microwave background is therefore both smooth and uneven. These temperature differences also preserve information about sound waves in the primordial plasma. Before neutral atoms form, matter and radiation are tightly coupled. Gravity attempts to compress denser regions, while the pressure of radiation pushes outward. This creates oscillations, waves of compression and expansion moving through the young universe. They are not sound in air, but pressure waves travelling through plasma. When the universe becomes transparent, the pattern is frozen into the distribution of matter and radiation. The sizes of the warm and cool regions in the microwave background reveal the scale of those ancient oscillations. From them, scientists infer the geometry, composition, and expansion history of the cosmos. The first accidental detection of this afterglow begins with an unwanted hiss. A sensitive radio antenna records noise that persists no matter where the instrument points. Local explanations are tested and removed. Equipment is checked. Sources of interference are considered, and contamination inside the antenna is cleaned away. Still, the signal remains. It arrives from every direction with nearly the same strength. The noise is not a fault in the instrument. It is radiation filling the sky. The discovery provides the missing observational support for a universe that begins in a hot, dense state, and then expands and cools. A steady universe with no hot beginning has difficulty explaining such a universal thermal afterglow. The early fire is no longer only a mathematical reconstruction. Its cooled radiation is present in the space around every planet and star. Later observatories map the background with increasing precision. Instruments above the atmosphere avoid much of the interference that affects measurements from the ground. They reveal that the radiation follows an almost perfect blackbody spectrum, the characteristic distribution of light from matter in thermal equilibrium. Instead, the background behaves as expected for radiation once immersed in a hot, dense plasma and then stretched by cosmic expansion. More detailed maps show the tiny temperature fluctuations across the sky. These maps appear mottled, with warm and cool patches, but the differences are extremely small. The image resembles a portrait of a universe that is still simple, before stars ignite in large numbers, yet already contains the pattern from which later structure will grow. The background also reveals the contents of the cosmos indirectly. Ordinary atoms influence the acoustic pattern. Dark matter contributes gravity without interacting strongly with light, shaping how the waves develop. Cosmic geometry changes how the pattern appears across the sky, while expansion affects the radiation during its journey. By combining these effects, scientists estimate the proportions of ordinary matter, dark matter, and the energy associated with accelerated expansion. The atoms that form stars, planets, gas, dust, and living bodies make up only a small fraction of the total cosmic inventory. Most matter appears to be dark and known mainly through gravity, while an even larger component is linked to the accelerating expansion of space. The oldest visible light therefore reveals how incomplete the familiar material world is as a description of the whole universe. Yet the afterglow has limits. It shows the universe after nuclei and electrons combine into atoms, not the earlier instant when space, time, and matter enter their earliest known state. To study earlier periods, cosmology must rely on indirect traces, the abundance of light elements, the distribution of galaxies, possible gravitational waves, and the consequences of physical theories. The microwave background is a horizon, not the final origin. Its surface marks the point beyond which ordinary light cannot carry a direct image. Even so, it reaches farther into the past than any star. Every galaxy observed through a telescope belongs to a later chapter. The background comes from a time when the universe has no mature galaxies at all. It is a field of ancient evidence beneath every later light source. As the photons travel, their paths are bent by gravity, and some scatter from free electrons released when the first stars alter surrounding gas. These later effects add information about the growth of structure and the emergence of luminous objects. The background is not only a preserved snapshot, it is also a screen upon which later cosmic history leaves faint marks. Its photons begin their journey when atoms first become stable, then cross an evolving universe until they enter detectors built from heavy elements, forged in stars that do not yet exist when the journey begins. The observation closes an immense circle. Ancient hydrogen releases light. Stars later build complex matter, planets form, and matter on one small world eventually constructs instruments able to detect the original glow. The cosmic microwave background turns the darkness between stars into something less empty. Space is filled with old radiation, cooled almost to silence but never erased. Its nearly uniform glow remembers the first atoms. Its slight irregularities anticipate the first galaxies. It stands between the simple chemistry of the early universe and the complex architecture that follows. The next transformation begins when gravity acts on those small differences for millions of years, drawing hydrogen and helium into denser regions until the first stars ignite. In their cores, the universe discovers a new way to build matter, and the long age of stellar alchemy begins. The first stars begin with almost nothing but hydrogen, helium, and gravity. No earlier generations have enriched the gas with carbon, oxygen, silicon, or iron. There are no rocky grains to cool the clouds efficiently, no metals to shape their collapse, and no planets waiting around them. Matter gathers from the simple mixture left by the early universe, sinking into regions where density is slightly greater than the surroundings. Gravity amplifies every small advantage. A cloud that is only a little denser draws in more gas, grows heavier, and contracts more strongly. As it contracts, its center heats. The first stellar furnaces ignite inside these dark concentrations, transforming the simplest elements into a more varied chemical world. These stars are not merely the earliest lights. They are the first places where the universe begins to manufacture complexity. Without heavier elements to assist cooling, primordial gas behaves differently from the gas in later galaxies. Hydrogen atoms can radiate some energy, while hydrogen molecules provide another cooling path, but the process is limited. The collapsing clouds therefore tend to remain warmer and fragment into larger pieces. Many of the first stars are probably much more massive than the Sun, though the exact range remains uncertain because no individual member of that first generation has yet been observed directly. Their masses create fierce gravity, central pressure, and short lives. They consume nuclear fuel rapidly, shining intensely for only a small fraction of the time enjoyed by stars like the Sun. At first, they fuse hydrogen into helium, following paths determined by temperature and composition. In stars that contain carbon, nitrogen, and oxygen, those elements can act as catalysts in a cycle that converts hydrogen into helium. The first stars begin without such catalysts, so their early fusion relies mainly on reactions between protons. As helium accumulates and the core contracts, temperature rises. Eventually, helium nuclei begin to participate in a crucial process. Two helium nuclei can combine briefly to form an unstable beryllium nucleus. This structure usually falls apart almost at once, but in the dense core of a star, a third helium nucleus can arrive before the breakup occurs. The three helium nuclei then form carbon. This sequence, called the triple alpha process, crosses a gap that the early universe cannot bridge. There are no stable nuclei with certain intermediate masses, so carbon cannot be built efficiently during primordial nucleosynthesis. Stars solve the problem by holding helium at high density and temperature for long enough that a rare three-stage sequence becomes continuous. Carbon enters the universe through this narrow nuclear doorway. The process succeeds because carbon possesses an excited nuclear state at an energy that strongly increases the probability of formation under stellar conditions. Without this resonance, the production of carbon would be far less efficient. Once carbon exists, it can capture another helium nucleus and become oxygen. The relative rates of carbon creation and oxygen creation matter greatly. If nearly all carbon were converted into oxygen, the later chemistry of life would be very different. If oxygen were scarce, water and rocky planetary materials would also be changed. The actual balance emerges from precise nuclear properties and the evolving conditions within stars. Carbon and oxygen are therefore not random additions to the periodic table. Their cosmic abundance reflects the structure of nuclei and the temperatures reached during helium burning. As stellar cores grow hotter, further reactions become possible. Carbon nuclei collide and combine, producing elements such as neon, sodium, and magnesium through several pathways. Neon can be broken apart by energetic radiation and rearranged into oxygen and magnesium. Oxygen fusion creates silicon sulfur and related nuclei. Silicon burning then drives matter through a dense network of captures, breakups, and rearrangements toward the iron group. The sequence does not operate identically in every star. Mass controls the central pressure and temperature, while composition, rotation, mixing, and mass loss alter the details. Lower mass stars may never reach carbon ignition. Stars similar to the Sun create carbon and oxygen in late stages, but do not proceed through the full chain to iron. Only more massive stars generate conditions severe enough for successive fuels to burn in the core and surrounding shells. A massive star near the end of its life becomes chemically layered. Hydrogen continues to fuse in an outer shell. Deeper inward, helium burns. Beneath that region, carbon, neon, oxygen, and silicon occupy progressively hotter zones. The structure resembles a record of nuclear history arranged by depth. Each shell marks a fuel that once dominated the center before being displaced by heavier material. The innermost region moves toward iron group nuclei, while the outer layers preserve lighter products. Convection and other mixing processes carry material between regions, changing how much of each element is produced and where it remains. Some newly made nuclei reach the surface before the star dies, especially when strong stellar winds strip away outer layers. In this way, stars begin enriching space even before their final collapse. The phrase stellar factory can suggest a clean assembly line, but the reality is more turbulent. Stellar interiors are moving plasmas shaped by pressure, radiation, rotation, magnetic fields, and unstable flows. Reaction rates depend steeply on temperature, so small changes can produce large differences in energy generation. Convection can transport fuel inward and ashes outward. Shells can expand, contract, or ignite unevenly. Material may be lost through winds, exposing deeper layers that were once hidden. In evolved massive stars, the surfaces can display products of internal fusion because much of the original hydrogen envelope has been removed. Their spectra reveal carbon, nitrogen, oxygen, and other elements that have been processed in the interior. The star announces its hidden chemistry through the light absorbed and emitted by its outer gas. The chemical products of one generation also change the behavior of the next. Heavier elements improve the ability of gas to radiate energy and cool, encouraging clouds to fragment into smaller pieces. Dust grains form from enriched material and provide surfaces on which molecules can assemble. Stellar populations become more diverse, and planetary systems become increasingly possible. The universe does not repeatedly form identical stars from an unchanged mixture. Each generation inherits material altered by the generations before it. The first stars alter more than chemistry. Their ultraviolet radiation ionizes surrounding hydrogen, separating electrons from nuclei and creating expanding bubbles of hot plasma. Their winds and explosions stir the gas, while their gravity contributes to the assembly of early galaxies. Yet their chemical legacy remains among the most durable effects. Carbon permits complex molecular frameworks. Oxygen becomes part of water, silicate minerals, and countless compounds. Silicon and magnesium help form rocky worlds. Calcium enters minerals and, much later, living structures. Iron contributes to planetary cores and biological chemistry. These later roles are not the purpose of stellar fusion, but they reveal how nuclear processes open possibilities at larger scales. The elements are created without anticipation, yet once released they allow matter to organize in new ways. Observations of very old stars preserve clues to the earliest enrichment. Some ancient stars contain small amounts of iron but measurable carbon or other light elements. Their compositions may reflect the yields of only one or a few earlier stellar explosions. By comparing these patterns with models of massive primordial stars, researchers attempt to infer the lives and deaths of objects that no longer exist. The oldest surviving stars become chemical archives. Their atmospheres contain atoms formed before the galaxy reaches its present shape, though the interpretation of each pattern remains uncertain. Stars also produce radioactive nuclei that later decay into more stable elements. Their daughter products can survive in meteorites, preserving evidence that stellar nucleosynthesis continues close in space and time to the birth of planetary systems. The transformation from hydrogen to heavier elements remains incomplete inside ordinary stellar burning. Fusion builds much of the sequence up to the iron region. But many nuclei beyond iron require a different method. Their creation depends less on adding charged nuclei and more on capturing neutrons, which can enter nuclei without facing electrical repulsion. Some neutron capture occurs slowly in aging stars, while other production requires a sudden and overwhelming flood. The stellar factory therefore has more than one workshop, and some operate only in the final instability of stars or in collisions between their remnants. Before those extreme events begin, stable burning establishes the essential middle of the periodic table. From helium, it produces carbon. From carbon and helium, it produces oxygen. Through hotter stages, it builds the materials of rock and metal. The first stars begin as simple clouds left by the Big Bang, but they do not remain simple. Their cores become places where the universe revises its own composition. When these stars release their products, space is no longer chemically young. The next clouds contain the ashes of a nuclear history, and the next generation forms from a richer inheritance. Complexity begins in stellar darkness, then waits for death to carry it outward. A massive star does not end because its light simply fades. It ends when the balance that has supported it for millions of years can no longer be maintained. Deep in the center, fusion has built a core dominated by iron group nuclei, matter so tightly bound that further fusion does not release useful energy. Gravity continues to press inward, but the nuclear furnace has reached its limit. The core grows heavier as surrounding shells continue to burn and add fresh material. Temperature rises, density increases, and the star approaches a threshold beyond which no ordinary pressure can hold it. The final collapse begins in a region smaller than the star itself, yet the consequences race outward through layers spanning millions of kilometers. Stellar death becomes an event of cosmic construction. As the iron core contracts, electrons are forced into protons, producing neutrons and neutrinos. This process removes electrons that had helped provide pressure, weakening one of the last supports against gravity. At the same time, intense radiation breaks iron nuclei apart, consuming energy and reducing resistance further. The collapse accelerates. Matter falls inward at a significant fraction of the speed of light, and the core density rises toward that found inside atomic nuclei. Protons and electrons merge in vast numbers, leaving a compact mass rich in neutrons. The central region becomes so dense that the strong nuclear force and quantum pressure resist further compression. Infalling material strikes this suddenly stiffened core and rebounds, creating the beginning of a shock wave. Yet the rebound alone is not enough to guarantee an explosion. The shock loses energy as it tears apart heavy nuclei in the surrounding layers. Neutrinos stream from the forming neutron star, carrying away most of the gravitational energy released during collapse. Although neutrinos interact only weakly with matter, their numbers are so enormous that a small fraction deposits energy behind the stalled shock. Convection, turbulence, rotation, and magnetic fields may also help revive it. In many massive stars, the shock regains strength and drives outward, disrupting the star in a core collapse supernova. The outer layers are accelerated into space, while the inner remnant becomes a neutron star or, if the core is heavy enough, continues collapsing into a black hole. The explosion lasts only a short time, but its light can rival that of an entire galaxy. This brilliance comes not from ordinary fusion alone, but from the conversion of gravitational energy, the heating of ejected gas, and the radioactive decay of unstable nuclei produced during the event. Nickel isotopes form in the hottest regions and later decay through cobalt into iron, releasing energy that keeps the expanding debris luminous after the initial shock has passed. The fading light curve becomes a record of nuclear change. Even after the star is destroyed, radioactive atoms continue to shape what can be observed. Supernovae are often described as the birthplaces of heavy elements, but the truth is more varied. Many elements up to the iron region are created during the star's long life and are simply expelled by the explosion. Others are synthesized or rearranged in the shock-heated layers during the final event. Some heavier nuclei form through rapid neutron capture, in which atomic nuclei absorb neutrons faster than they can undergo radioactive decay. Because neutrons carry no electrical charge, they can enter already heavy nuclei without facing the strong repulsion that blocks charged particles. The nucleus becomes increasingly neutron-rich, then later transforms through beta decay, converting some neutrons into protons and moving towards stable heavy elements. This rapid process can create a wide range of nuclei beyond iron, though the exact contribution of ordinary core collapse supernovae varies with the explosion conditions. Some rare stellar explosions, highly magnetized outflows, and the collisions of neutron stars may provide especially favorable environments for producing the heaviest elements. The neutron star left behind is itself an object of extraordinary density. A mass greater than that of the Sun may be compressed into a sphere only tens of kilometers across. Inside, matter exists in forms that cannot be reproduced easily in laboratories. The outer layers contain nuclei packed among free electrons. Deeper regions may hold superfluid neutrons, superconducting protons, and perhaps more exotic states. The star can rotate rapidly and produce beams of radiation from its magnetic poles. When those beams sweep across Earth, the object appears as a pulsar, a signal repeating with remarkable regularity. The quiet pulse is the surviving rhythm of a vanished giant. If the collapsing core exceeds the limits of neutron pressure, even this compact state cannot endure. Gravity continues inward, forming a black hole. Some stars may collapse with weak visible explosions, while others produce energetic outflows along their rotational axes. The final result depends on mass, metallicity, rotation, magnetic fields, and the amount of material lost before collapse. Yet all endings alter the surrounding universe. The ejected gas moves outward at thousands of kilometers per second, driving shock waves into interstellar space. It heats nearby material, compresses clouds, amplifies magnetic fields, and stirs the gas between stars. A supernova remnant expands for thousands of years, forming glowing filaments and shells enriched with oxygen, silicon, sulfur, iron, and other products of stellar burning. The debris does not remain a uniform cloud. Different layers move at different speeds. Dense knots survive, radioactive nuclei decay, and collisions with surrounding gas produce radiation from radio waves to X-rays. By mapping these remnants, scientists reconstruct the internal layers of the original star. Matter that was once buried in the core becomes visible across a widening nebula. Destruction reveals the star's hidden anatomy. The outward shock may also trigger new star formation, though the process is not automatic. A shock can compress a nearby molecular cloud until gravity takes over, but it can also heat or disperse gas and prevent collapse. The same explosion can create and erase possibilities in different regions. Over long periods, the enriched debris mixes with the interstellar medium. Atoms produced in separate stars become part of shared clouds. Some are swept into later stellar systems. Others drift for millions of years before entering new planets, comets, or living organisms. A young planetary system may inherit material from several earlier stars, each contributing a different set of isotopes. Meteorites preserve tiny grains that formed around ancient stars before the solar system existed. Their unusual isotope ratios identify them as pre-solar material, direct fragments of vanished stellar environments. The death of giant stars therefore leaves evidence not only in distant remnants, but inside rocks that reach planetary surfaces. Supernovae also influence galaxies on the larger scales. Their explosions inject energy into interstellar gas, helping regulate how quickly galaxies form new stars. Repeated events can drive hot material out of galactic disks and into surrounding halos. In small galaxies, powerful stellar feedback may remove a large fraction of the available gas. In larger systems, the gas may cool and fall back later, carrying metals into new regions. Astronomers call all elements heavier than helium metals, even when they are not metallic in ordinary chemistry. The metallicity of stars records how many generations of enrichment have occurred before they formed. Very old stars contain little iron and preserve the chemistry of an early galaxy. Younger stars often contain more heavy elements because many earlier stars have already lived and died. Galactic history becomes a history of repeated stellar recycling. Yet a supernova is not only a source of abundance, it can also be a source of danger. Close enough to a living world, intense radiation and energetic particles could damage atmospheres and alter surface conditions. At greater distances, the same event may deliver useful isotopes without causing destruction. Cosmic creation and cosmic hazard arise from the same process. The elements required for rocky planets and biology are scattered by events capable of sterilizing nearby worlds. Nature does not separate construction from violence. The same collapse that ends one star enriches the material from which later stars and planets form. The ashes of the explosion continue outward, cooling and mixing until their origin becomes difficult to trace. Iron from one star may settle into a planetary core. Calcium from another may enter a shell or bone. Gold produced in an extreme neutron-rich event may become part of a mineral vein. Their isotope patterns preserve the routes by which they were made. A giant star reaches its final limit at iron, collapses in seconds, and distributes the work of millions of years across space. Its death changes the chemical future of regions it will never occupy. Destruction becomes distribution, and the universe moves from stellar furnaces toward enriched clouds, where the next generation of stars, planets, and galaxies will take shape. The debris of dead stars does not remain scattered forever. It enters the vast circulation of matter that moves through galaxies, mixing with hydrogen, helium, dust, and radiation until gravity gathers it again. The universe builds by reuse. Gas expelled by stellar winds and explosions cools within interstellar space, while heavier elements condense into tiny grains. These grains drift through magnetic fields, collide with molecules, and become part of dark clouds where new stars may form. Material from many earlier stars overlaps, and each cloud carries a mixed inheritance. Some atoms formed during the first minutes of the universe. Others were assembled in quiet stellar cores. Still others were created in violent collapses or neutron-rich events. When gravity draws them together, separate histories become one new system. Galaxies provide the environments in which this recycling continues. A galaxy is not merely a collection of stars. It is a changing structure of stars, gas, dust, dark matter, magnetic fields, radiation, and compact remnants held together by gravity. Spiral galaxies contain rotating disks, central bulges, and extended halos. Elliptical galaxies contain older stellar populations arranged in rounded forms with relatively little cool gas. Irregular galaxies often bear the signs of gravitational disturbance. These categories describe appearances rather than fixed destinies. Galaxies grow, collide, lose gas, acquire gas, and change shape. Their stars follow different orbits, their gas responds to pressure and shock, and their dark matter forms an unseen framework that strongly influences their motion. The visible galaxy rests inside a much larger gravitational structure. Dark matter does not emit or absorb light in ordinary ways, but its presence is inferred from how stars and gas move and how light bends around massive systems. In many galaxies, visible matter alone cannot explain the observed orbital speeds. Stars far from the center move too quickly to remain bound by the gravity of luminous material. A broad halo of unseen mass supplies the additional attraction. In the early universe, dark matter also helps small density differences grow. It gathers into clumps before ordinary gas can cool efficiently, creating gravitational wells into which hydrogen and helium fall. Galaxies begin inside these wells, where gas compresses, cools, and forms the first generations of stars. Small systems merge into larger ones. Streams of stars preserve the remains of galaxies that have been torn apart. Galactic halos become archives of ancient construction. Within a galactic disk, clouds do not collapse merely because they contain gas. Internal pressure, turbulence, magnetic fields, and stellar radiation resist gravity. A cloud begins forming stars only where enough material gathers into a sufficiently cold and dense region. Molecules become common in the darkest parts, especially molecular hydrogen. Dust blocks external light, shields molecules from destructive radiation, and allows gas to cool more effectively. As cooling reduces pressure, gravity gains influence. Dense knots form within larger clouds, and some contract into protostars. Each protostar draws material inward through a rotating envelope. Because the original cloud possesses even a small amount of angular momentum, the infalling matter cannot move directly into the center. It spreads into a disk. Rotation becomes organized as the system contracts, and the young star grows at the center, while the surrounding protoplanetary disk becomes the setting for planet formation. The disk contains mostly gas, but the heavier elements from earlier stars are crucial. Carbon, oxygen, silicon, magnesium, iron, and other elements form molecules, ices, and mineral grains. Tiny particles collide and sometimes stick through electrical forces. They grow into larger aggregates, though the path is complicated by fragmentation, drift, and turbulence. Some concentrations become large enough for gravity to strengthen their growth. Kilometre-scale bodies, called planetesimals, collide and merge into planetary embryos. Over millions of years, these embryos sweep through the disk, scatter one another, and settle into a smaller number of planets. Close to the young star, high temperatures favour rock and metal. Farther out, colder conditions allow water, methane, ammonia, and other volatile compounds to freeze. This broad temperature pattern helps produce rocky inner worlds and more massive outer planets rich in gas and ice, though migration and collision can rearrange the final system. Planet formation is not a calm sequence of perfect circles. Young systems are dynamic. Growing planets alter the disk, opening gaps and exchanging angular momentum with gas. Their orbits shift. Some bodies fall into the star, while others are thrown outward or ejected into interstellar space. Collisions can strip atmospheres, melt surfaces, create moons, or combine worlds. Even after the main planets form, smaller bodies continue to deliver water, carbon compounds, and metals. Asteroids and comets preserve primitive material that changed less than the interiors of planets. They retain clues to the cloud from which the system formed and to the stellar sources that enriched it. A planet is thus a concentrated sample of galactic history. Its core, mantle, crust, atmosphere, and oceans separate according to the physical and chemical properties of inherited atoms. Dense iron sinks during early melting. Silicate minerals build mantles and crusts. Volatile molecules gather into atmospheres and surface reservoirs when temperature and gravity permit. The same elements behave differently under different conditions, producing worlds of metal, rock, gas, ice, or mixtures of them. The architecture of a planetary system reflects the mass of its star, the composition of its disk, the timing of formation, and the chance outcomes of encounters. Yet all systems depend on previous stars. A universe containing only hydrogen and helium could form stars and perhaps simple gas giants, but it could not easily build rocky planets, mineral surfaces, or carbon-rich chemistry. Stellar generations increase the possibilities available to matter. Galaxies regulate this enrichment. Regions with rapid star formation produce heavy elements quickly, but they also generate strong winds and explosions that may expel gas. Quiet regions preserve gas longer, but enrich it more slowly. Large galaxies can retain more of their material, while small galaxies may lose it through energetic outflows. Collisions between galaxies compress some clouds and trigger bursts of star formation while disrupting others. When galaxies merge, individual stars rarely collide because the distances between them are immense, but their gravitational orbits change and their gas clouds interact strongly. Tidal forces stretch long streams of stars and gas. A merger can transform disks into more rounded systems, though gas may later settle into a new disk. Galactic form emerges from repeated interaction rather than isolated growth. At the centers of many large galaxies lie supermassive black holes. When gas falls toward one, it forms a hot accretion disk and can produce brilliant radiation. Jets and winds carry energy outward, affecting the gas from which stars might otherwise form. This feedback can limit growth, stir the galactic atmosphere, or push material into surrounding space. A black hole occupies a tiny region compared with its galaxy, yet its activity can influence matter across enormous distances. Galaxies themselves gather into groups, clusters, filaments, and walls. Between these structures lie vast voids containing far less matter. This cosmic web grows from the slight density variations recorded in the ancient background radiation. Gravity amplifies them over billions of years. Dark matter forms an underlying network. Ordinary gas flows along its filaments, and galaxies collect where the network is densest. Clusters become filled with hot gas, heated by gravitational collapse and galactic activity. Much of the ordinary matter in these regions exists not inside stars, but between galaxies in diffuse, ionized form. The visible points of light reveal only part of the structure. From atoms to planetary disks, from stars to galactic arms, and from galaxies to the cosmic web, matter organizes through repeated layers of attraction, motion, cooling, and feedback. Each larger scale depends on rules operating below it, but no scale is merely a magnified copy of another. Nuclear forces create stable elements. Electromagnetic forces create atoms, molecules, dust, and chemistry. Gravity gathers large masses and shapes stars, planets, galaxies, and clusters. Rotation preserves memory of earlier motion. Radiation heats and cools matter. Explosions enrich and disturb it. The universe is built not by one force acting alone, but by forces dominating at different scales and connecting through time. A galaxy is therefore both structure and process. It contains ancient atoms, living stars, dead remnants, forming planets, drifting gas, and unseen mass in continuous exchange. Its shape may appear permanent across a human lifetime, yet it is evolving. Stars migrate through the disk. Satellite galaxies fall inward. Gas arrives from the surrounding web or escapes in winds. New stars ignite from enriched clouds, while old stars return material to space. The galaxy becomes a vast engine of circulation, turning primordial simplicity into repeated generations of complexity. Within that circulation, the atoms of future oceans, mountains, and living cells wait in darkness until gravity gathers them into another sun. The universe is built in layers, but its history remains present in the smallest pieces. A galaxy may contain hundreds of billions of stars, and a planet may contain mountains, oceans, clouds, and living systems. Yet every visible structure depends on atoms whose origins reach far beyond the place where they now exist. Some atoms begin in the first minutes after cosmic expansion starts. Others form inside stars that no longer shine. Some are released by winds from aging suns, while others emerge from explosions or collisions so violent that space itself is flooded with neutrons, radiation, and newly assembled nuclei. These atoms travel, mix, cool, and gather again. They enter new stars, new worlds, and new chemical arrangements. The matter of the present is therefore a record of many separate times joined together. Hydrogen carries the oldest story. Most hydrogen nuclei form when the universe is still young enough to be measured in minutes. They survive the rise of galaxies, the birth and death of countless stars, and the formation of planets. Some remain in interstellar clouds, some become fuel in stellar cores, some combine with oxygen to form water, moving through oceans, atmospheres, ice, rock, and living cells. A hydrogen atom in a drop of water may be nearly as old as ordinary matter itself. Its nucleus persists while its surroundings change repeatedly. It may join one molecule, separate, drift, react again, and enter another system. Chemical bonds are temporary arrangements, but the nucleus can endure through immense spans of time. Helium also begins largely in the early universe. It fills stars and gas clouds, often remaining chemically inactive because its electron structure is already stable. Yet inside stellar interiors, helium becomes the gateway to complexity. 3 helium nuclei can combine through a rare sequence to create carbon. That carbon may capture another helium nucleus and become oxygen. Heavier stars continue the process, moving through neon, magnesium, silicon, sulfur, and the iron group. The simple mixture left by the Big Bang becomes a richer inventory only because gravity compresses matter into stars. Gravity does not create the elements directly, but it builds the conditions in which nuclear forces can transform them. The history of matter is therefore a collaboration between forces operating at different scales. Gravity gathers, electromagnetism shapes atoms and chemistry. The strong force binds nuclei. The weak force permits crucial transformations. No single force builds the universe alone. Carbon carries a particularly wide range of the later possibilities. Its electron structure allows stable bonds with several other atoms and with itself, producing chains, rings, sheets, and branching frameworks. In interstellar clouds, carbon appears in simple molecules and dust grains. In planetary systems, it enters atmospheres, minerals, ices, and organic compounds. On Earth, it becomes central to the chemistry of life, cycling through air, ocean, soil, rock, and cells. Yet the carbon nucleus does not acquire this role because it is alive. It forms in stars long before biology exists. Its later usefulness emerges from atomic structure, environmental conditions, and long sequences of chemical selection. The carbon in living tissue is stellar matter organized into a temporary pattern capable of metabolism, repair, reproduction, and memory. The pattern is new, but the atoms are ancient. Oxygen follows a similar path. It forms mainly through stellar fusion and becomes one of the most abundant heavy elements in the cosmos. It joins silicon and metals in rock, combines with hydrogen in water, and participates in chemical reactions that release or store energy. Much of Earth is built from oxygen bound inside minerals rather than floating freely in the atmosphere. The oxygen in a breath may once have been part of carbon dioxide, seawater, stone, or living tissue. Before reaching Earth, its nucleus may have formed in a star that ends before the solar system begins. The atom changes partners but preserves its identity. Its history crosses environments that bear almost no resemblance to one another. Iron carries the memory of a more advanced stellar stage. It forms near the end of energy-producing fusion in massive stars and through the decay of unstable nickel created during stellar explosions. Later, gravity and chemistry give iron new roles. In young rocky planets, much of it sinks toward the center, helping create dense metallic cores. In Earth, moving liquid iron contributes to a magnetic field that extends into space. Smaller amounts remain near the surface, where iron enters minerals and biological molecules. In blood, iron helps a complex protein transport oxygen. The same element that marks a nuclear limit inside a dying star becomes part of a system that supports animal life. These roles are separated by billions of years and by enormous changes in scale. Yet they belong to one continuous material history. Elements heavier than iron often carry even rarer origins. Some form through slow neutron capture in aging stars, where nuclei gradually absorb neutrons and later transform into heavier elements. Others require rapid neutron capture during explosive events, or mergers involving neutron stars. Gold, platinum, and uranium do not emerge from ordinary stable fusion in a calm stellar core. Their nuclei require pathways beyond the iron peak, where energy, neutron density, and time combine in unusual ways. When such atoms enter a planet, their abundance is small, but their history is extreme. A grain of gold may contain matter assembled during an event that briefly outshines entire stellar systems. Uranium may become trapped in rock, where its slow radioactive decay releases heat and provides a clock for geological time. Cosmic violence becomes a quiet signal inside stone. The solar system itself forms from a cloud already enriched by earlier generations of stars. Most of its mass becomes the sun, while a small fraction remains in a disk and forms planets, moons, asteroids, and comets. The chemical differences among these bodies reflect temperature, distance, collision, and chance. Rocky planets gather refractory materials that withstand heat. Outer regions preserve more ice and volatile compounds. Meteorites retain primitive grains older than planets, including particles that formed around stars predating the Sun. Their isotope patterns reveal distinct nuclear sources. The solar system is not made from the remains of one star alone. It is a mixture drawn from a galactic reservoir shaped by many lives and deaths. Earth then transforms that inheritance through melting, differentiation, volcanism, erosion, plate motion, atmospheric change, and biology. Atoms move continually between reservoirs. Carbon enters rock, air, ocean, and cells. Water circulates through cloud, river, ice, and mantle. Iron shifts through minerals, magma, organisms, and sediments. Calcium passes through seawater, shells, limestone, bone, and soil. The planet does not manufacture these nuclei. but it reorganizes them through chemistry and geology. Life becomes one of the most intricate forms of that reorganization. A living body is not a fixed collection of atoms. Matter enters, participates for a time, and leaves. The structure persists through exchange. The atoms remain older than the organism and continue after it ends. This continuity changes the meaning of origin. No single moment creates the material of a living system. The atoms arrive from different cosmic eras, the molecules assemble through planetary chemistry, and biological organization emerges within environments shaped by geology and earlier life. The result is local, but its ingredients are universal. Every cell contains hydrogen from the early cosmos, carbon and oxygen from stars, phosphorus from stellar nucleosynthesis, iron from advanced burning and decay, and trace elements shaped by rare nuclear events. The body is not separate from cosmic history. It is one temporary arrangement within it. Galaxies preserve the larger circulation. Stars form from gas, alter it, and return part of it to space. New stars inherit the products. Planets condense from enriched disks. Some systems are destroyed, others survive, and matter continues moving. Even atoms locked inside long-lived stars or drifting between galaxies remain part of the same evolving inventory. The universe builds complexity not by replacing its foundations, but by rearranging them. The earliest nuclei become the fuel of stars. Stellar ashes become planets. Planetary chemistry becomes life. Life returns matter to air, water, and soil. At every stage, the form changes more readily than the underlying particles. The path from atoms to galaxies therefore closes without becoming complete. Galaxies organize matter on immense scales, but they also create the environments where atoms enter new histories. The smallest pieces preserve the larger story, while the largest structures determine where the smallest pieces travel next. The universe is built through this exchange between scale and time, between ancient nuclei and new arrangements. Nothing visible is entirely new, and nothing remains in one form forever. Matter carries the past forward, quietly assembling worlds from remnants, light from mass, and living complexity from atoms that once moved through the hearts of stars.